My name's Austin Harris. I'm a performance engineer at Oak Ridge National Laboratory. I'm here with Eirik Endeva, who's also at Oak Ridge. I'm going to talk a little bit about the experience with the ExoStar application Thornado and our efforts to port it to GPUs to perform well, to perform spectral neutrino transport. So a little bit of background about our application. So ExoStar is the ECP project that's based off this idea of a component-based, multi-physics, AMR-based toolkit for simulating stellar explosions, like supernovae neutron star mergers. And so we have lots of nice observations of those, like these images on this slide. To do this, we have to couple a lot of different physics in a single code. And the approach that we're taking is to use the AMR-based FlashX code, which is predominantly written in Fortran. And our approach has been to use compiler directives, so primarily OpenACC and OpenMP, and then using some vendor-optimized math libraries for things like linear algebra when possible. So as the title alludes to, one of the physics modules that we're worried about is spectral neutrino transport, and we're particularly concerned about it because it really contains most of the flops and the cost of these simulations. And so there are other modules too, like nuclear burning and MHD, and we're taking a similar approach in all of these, but today I'm going to talk about the neutrino transport. So to do that, we use a code called Thornado, which is a kind of a modular code that's intended to be used in AMR-based codes like FlashX. But we try to solve this equations for spectral neutrino transport and astrophysics simulations. And because it's really designed to be incorporated into these other AMR-based codes, the focus that in our Thornado development is really on maximizing the single MPI rank and GPU performance. And then we let the AMR framework kind of manage the load balancing and domain decomposition. So also, in addition to the neutrino transport, there's some microphysics that are included and I'll talk a little bit about those in the slides that are coming up. But these come from another code called weaklib that's maintained and developed by the same people. But it's also intended to be modular across different applications. And so the original CPU code had no GPU support. And so our approach was to use compiler directives and libraries. And oftentimes that also required rewriting existing code and to put it in a better format to use GPUs. The setup for the problem here is that we have these finite volume blocks from something like FlashX. And then we do a phase-based discretization on top of those blocks where we split a single AMR block up into spatial elements and then nodes within each block. And then also in energy space, we apply a DG discretization as well. And then to couple this in Flash, there's a time integration that uses something called an implicit-explicit or IMEC scheme. And then within each IMEC step, there are some discrete pieces of Thornado that are executed. So there's an explicit neutrino advection operator, which is limited by the crossing time at the speed of light. And then there's also an implicit neutrino collision operator that has a nonlinear solver in it. And that's where most of the flops of Thornado and most of the time is spent. And then there are also some numerical limiters that are used to maintain realizability. But each one of these has kind of distinct challenges to how we had to approach getting performant GPU code. So this is an OpenACC talk, so I'll give a little bit of a talk about what kind of features we're using in OpenACC. So most of the work that we're doing are in the form of tightly nested loops, and then we just use the combined parallel loop gain vector collapse. And that works really well for 80 to 90% of the work we're doing, and we don't have to really think more about it. Also, we use a lot of unstructured data regions that we manage with enter data and exit data. And along the same regions, this is a Fortran code that has a lot of modules. And within those modules, there are variables that are also accessed in device functions. And so we have to use things like declare, create. And then I mentioned that we also use linear algebra libraries. And to do that, we have to interface between our OpenACC data structures and other API interfaces for the libraries. And to do that, we use the host data use device. Something else I'll say is that the async clause in OpenACC is really helpful and really gives us a boost in performance. But when we're doing, our regular development, it's something we don't usually, we usually leave it off because it can be, I've gotten myself into trouble once or twice trying to understand something and then forgetting that, oh, this is happening asynchronously. And so turning that off kind of helps me understand it a little bit more for development. Something that I'd really like to see in OpenACC in the future is a collapse clause that supports non-rectangular loopness, where the iteration count is known beforehand, but it's the inner loop may be iteration dependent. And so these are things like triangular loops, do j equals 1 to n, do I equals 1 to j. Those things can be manually unrolled, and that's the approach we've taken, but I think we'd get better performance with compiler support. And one of the things I'll say about OpenACC specifically is that one of the significant that I've found in development for Thornado of OpenACC over some other models is that there is a direct way to access the mapping to GPU streams. And that makes things like interfacing with libraries much more straightforward. So we have these generic library interfaces in Thornado for something like a batch linear solve or with LU decomposition. So that's something that can have a complicated interface, especially in Fortran. And so we kind of took this approach to any linear algebra libraries we use, we kind of wrap them in this generic interface. And so we try to keep the same interface that LAPACK or BLAS is already using. And then we come into the routine and see if the data is still there using this devices present function that we wrote that's really just a wrapper to whatever the offloading model that you're using. Whatever API that supports is what it uses. And so that's on the bottom left. And then depending on if the data is on the device, then we go ahead and set up, device pointer arrays that are needed for things like these batched library operations. And then we just use macros to determine at compile time to support multiple different libraries that, so we can examine which libraries perform better and make those choices. And then if the data is not on the device, it just falls back to a standard CPU library. Just a quick look at what some of our code looks like. I don't want to spend too much time on this, but this is one of the more expensive kind of kernels that we've had to deal with. And it's really a straightforward kernel when you think about it. There's not a lot going on here, but it comprises about 40% of the runtime. As you can see on the right, it's not a tightly nested loop, like I mentioned before. You could write this as a tightly nested loop, but we found it was better to break it into this kind of this double level of this two-tier level parallelism. And it has that collapsed triangular loop that I was talking about that we were unrolled and got a lot of performance gains from doing that, but it would have been nice to have the compiler support for that. And so this is an HBM memory bound kernel and I'll elaborate on that a little bit more soon. But you can see that because of this linear interp 2D function, we have these non-strided or these poorly strided memory access patterns for this table array in the outer dimensions. And there's really no way around that for us. And that means that we're doing a lot of having a lot of fetches from HBM memory. This is something that's called many times within a single Thornado time step. And so it's where we spent a lot of time drilling down and getting the best performance we could. And to kind of contrast that, this is kind of another example where this is a piece of code that had a lot in this original CPU code. It was one really big loop where each iteration was doing a ton of work, and it did not perform well on GPUs. And we had to break this up at the expense of using a little more memory, but getting a lot more instruction level parallelism. We took this big loop and broke it up into smaller loop. One of those, for example, contains a bisection iteration, which is not something that's going to perform well across on the GPU, because each point that's doing the bisection iteration could take a very different amount of time to converge. And so this is a kind of type of kernel that has low arithmetic density. And really the key to getting performance here was to try to break it up into small pieces that made sense. This is a benchmark that we did that tests the explicit operator, where this one is a mix of a lot of tightly nested loops and linear algebra libraries for matrix multiplication. And so we set this problem up to basically evolve what one AMR block would look like coming into Thornado. And so the phase-space discretization is the same. And we ran this on Summit using the NVIDIA compiler and also the IBM compiler for OpenMP offloading, and could kind of compare the results. And both of the compiler directives approaches had great speed up over the threaded CPU code. We found a little bit more of improvements with OpenACC, and I'd like to revisit this eventually using the same compiler with OpenMP offload support, and that's just something that we haven't got to yet. And I know that that's something that we can do now with the NVIDIA compiler. So this is another one of the operators. This benchmark tests another one of the operators in Thornado. This is testing the implicit operator. We call this the relaxation problem. And here we're also doing the same thing and running just on a single GPU with 7 power 9 cores and involving one block. And here, as I mentioned, this is really where most of the computation is being done in the Thornado step. And that is also shows up in the fact that we're able to get a much bigger speed up here for using the GPU relative to the GPU. I mean, 7 to 10x is great, but 30x is even better. And here we saw the same trend really where we were getting slightly better performance with OpenACC than OpenMP. And that seemed to hold regardless of the particular kernel that was being used. There were some kernels that do better than others, depending on the execution model, but the trend was definitely there for all of them. And so lastly, we really wanted to understand kind of why we were seeing the performance that we were, and kind of the gold standard for how to understand this is to look at a roofline model. And so we took that relaxation problem that I just showed and constructed a hierarchical roofline model based on for some of the bottleneck kernels that are taking the most of the computational time. And there were some themes really that showed up. So first is that Thornado was definitely memory bound, as we're not hitting the FMA or no FMA roofline on any of these. But on the plus, which is going to be a challenge as architectures move further and farther away from. This is going to be more of a challenge as we look to future architectures. But the good news is that for all of these kernels that we looked at, they are near the memory bandwidth roofline. So that at least says that our implementation of the method itself is performing well, but maybe there are some ways that we can think about different methods to use that would increase the arithmetic intensity so we could move closer to the floating point operation roofline. And then also we could think about things that we could tune within OpenACC execution model, perhaps maybe changing vector length and manually fine-tuning things that might be able to move those points further up that line as well. We also want to look and see how this is doing for newer hardware too. So to wrap up, this is something that we hear over and over again. If you write performance portable CPU code first, everything is easier. So that means, among other things, an example is having discrete type loopness, where you really are able to take advantage of vector level parallelism and instruction level parallelism. Reiterate, one of the challenges we had in all of this was porting kernels that had iterations in them. Nonlinear solver or root finders, those things were very challenging because they usually are large kernels and have a lot of register pressure. And so there's a couple approaches to that. One of them is to you just bite the bullet and have each thread basically run its own iteration. But the approach that we found for a lot of cases was better to try to break that iteration up and to separate smaller kernels. But that just requires an extra level of bookkeeping to keep track of points that have converged. I'll say that that the NVIDIA HPC compiler suite has been extremely useful for understanding performance at a very low buy-in level. Like there's something that's really easy to access and get feedback. So that comes from things like the compiler feedback, which is really helpful to know, how many registers are being used and what's being moved around in terms of data, how the kernels are being launched. And then there's also these very useful environment variables like NV compiler, ACC notify, that tells you very explicitly what data movement's happening, when are synchronizations happening. It's a lot to look through, but something that I've a few times found some synchronizations or data movement that I thought shouldn't be happening, but was because of some oversight. And lastly, improving performance oftentimes means rethinking the algorithms themselves, not just making one algorithm work well. And so this kind of falls back to what I was saying about we need higher arithmetic intensity if we're really going to maximize the performance gains that we see on new hardware that have even higher flop to bandwidth ratios. And so it'll be interesting, as we move forward to look and see how our performance changes on these systems. If are we still going to be close to the roofline, or how are we going to move along those performance analyses? Thank you everyone for coming.